Okay, so here are some examples. So these are the rules that I just sort of showed to you. So here's example number one. Let's say that I gave you this. So hopefully you would recognize this and say, well, the bases here are the same. The bases are the same, so you just get the exponent. So that's just going to give you 3. Sometimes we're a little sneaky. So in this case, it's not blatantly obvious that the bases are the same, but keep in mind that the natural log is defined as the log-based e. So in this case, you do see the e's match, so this is just going to be pi. Okay. Let's see, what else do we have? Let's go to a different rule. So what about the log 4 of 12 minus the log 4 of 3? So initially, you may not think much of this, but because you have a subtraction here, we can go backwards. So if you're given a subtraction, you can write it as a division. So this is actually the log 4 of 12 over 3, which is 12 divided by 3 is 4, right? And so now we're actually in rule number 2. The bases are the same, so this comes out as a 1. So this is where rewriting it would have helped you a little bit. Okay, we can do that the other way around. We could say that this could be the log 12 of 4 plus the log 12 of 36. So since we're adding here, that means we could write this as a single log with a multiplication. And 4 times 36 is 144, I believe. Yep. And so that's asking you for the following, so let's just put the y here now. So 12 to the exponent of y is supposed to be 144. So that means y equals 2. So your answer here is that this thing is actually worth 2. Okay, let's come up with another one. So here's another one. The log 3 of 5 times the log, sorry about that, but the log 5 of 9. Okay, this one initially you may not think much of, and this isn't the one, which is that? So this isn't related to this multiplication here. I know it says a multiplication, but we're not multiplying the 5 and the 9, we're multiplying 2 logs. But what you can do is say that, hopefully you can see that this base, this log 5, matches this 5 over here, and this 9 and this 3 have something to do with each other. And then we're going to borrow rule number 7 over here, which says that if you have a multiplication of two things, which we do, then you can shove one on top of the other. So let's just go do that and see what happens over here. So the log 5 of 9 to the exponent of the log 3 of 5. Now 9 is actually a 3 squared, right? So I could write this as the log 5 of 3 squared, and then that's to the exponent of the log 3 of 5. Well, these multiply, so that's the log based 5 of 3, and then that becomes 2 times the log 3 of 5. I'm going to use the rule again. This 2 is actually an exponent on the 5, so this is the log 5 of 3 to the exponent of log 3 of 5 squared, which is 25, right? And then over in here we have a little rule. Let's see if I can highlight it for you a little bit. This thing over here is actually a rule. If these bases are the same, then the number that you get out of the log this 3 log 325, because the whole thing is inside this, like it's the whole thing is the argument for the log of 5, log base 5. So this should just give you 25, in case you're wondering which rule I'm looking at right now. So the bases are the same. Let's see if I can make this a little bit smaller for you. So the bases are the same. The bases are the same. I should just get the m. So that's what I'm going to use. I'm going to say that this is the log 5 of 3 log 325 just gives you 25. And log 5 of 25 is just 2, because 5 squared is 25. So finally your answer here is 2. So that took a little bit more work. Okay, so you can see that these can get tricky because I'm definitely using more than one rule at a time right now. Okay, so let's do another one of those. So what if I asked you about the log 9 of 3x? Well, let's see where I can get if I do this. This is the log 9 of 3. And we're multiplying, so I can add to that the log 9 of x. So what does that mean? Well, that doesn't help me a lot, I guess, except that for this thing I actually know what that is worth. Because if I just look at the log 9 of 3 and call that y, then that would be 9 to the exponent of y is supposed to be 3. And either you can see here that that means you took the square root, or you can write this as a 3 squared, so this becomes a 3 to the 2y is a 3 to the first, so that means 2y is 1, so y is still a half. So you can plug that in over here. You can say that this is then a half plus the log 9 of x. And that may not look like it's much better, but at least we now split off a number out of this expression here, so technically we simplified a little bit. Okay. I think we got 2 more. So what about this one? The log 4 of 2x divided by 5. So what can you do with this? So if I just follow the rules, and this is the log 4 of 2x minus the log 4 of 5. So you can rewrite it that way. And keep in mind that, you know, perhaps we actually were given this initially. So let's say we were given this initially and I asked you to graph this. So what if I said, hey, graph y equals log 4 of 2x over 5? What would you do? Well, if you split it this way, then you can write this you can change this one more time. You can say that, well, I can use any base here, so let's use the natural log or the common log. So let's use a common log for this one. So the log 4 of 2x is the same as the log of 2x divided by the log of 4, which is your variable expression, minus the log base 10 of 5 divided by a log of 4. Now that expression can go in the calculator. So if I look at my first expression here, so this expression, I cannot use my calculator to graph. Now I don't know if that's true on GeoGebra. I don't know if you can use any base on GeoGebra, so we'll have to check that at some point. Excuse me. But this, I know I can put in GeoGebra because, you know, generally speaking, if you just type in log into the calculator or use the log button, it's the log 10. So this one is a log 10. That one's a log 10, so I can put those in the calculator. Log 10 of 5 I can put in, and a log 10 of 4 I can put in. So here's an expression that would be calculator or technology friendly. So sometimes we rewrite this stuff so that you can plug it in a calculator and see what you get out of it. So let's do one more of that. So let's say that I asked you to graph the following expression. the following function. Hey, I want to know what the log base 5 of the cube root of x squared plus 1 divided by x squared minus 1 looks like. Let's not worry about domains and all that, because that's a whole other question. So what could you do? Well, you could rewrite this as the log 5 of the cube root of x squared plus 1 minus the log base 5 of x squared minus 1. Let's actually use these over here. Then the cube root is an exponent, right? The cube root would be an x cubed plus 1 to the 1/3. And then on this side, x squared minus 1, that factors, so that's x minus 1 times x plus 1. So this would be 1/3 times the log 5 of x squared plus 1 minus the log 5 of x minus 1 times, so if I look at this whole thing together, then this splits in log 5 x minus 1 plus the log 5 of x plus 1. So I rewrote it on the fly, so it's distribute the negative, so that's minus log 5 x minus 1 minus the log 5 of x plus 1. So now I rewrote it into simpler parts, and that would allow me to maybe do some work with this. Okay? Alright, thank you.